excited about starting this one compared to that. I feel like this might have enjoyable.
Yeah,
This is fun.
Referring back to the
we had fun.
That wasn't the tone of voice I wanted. That
We had fun constructing it.
Was that what you were talking about in that lecture when it was just me, you, and Jan? You said, "Can I have question 2?"
Probably not. Probably not.
I remember
It might
hearing
be.
something along the
I
lines.
think we were deciding upon who was writing the solutions for.
For it.
Yeah.
Right.
Yeah, they haven't worked it out yet. They're going to do it now. Like, some of these could be unsolvable. They've not even looked at it.
There's a teacher at my.
There are various
high
levels
school.
you go through to, you can solve. You can kind of see, it's solved. Of course, it's maybe mistake things, but it's just a matter of who was writing it.
Because I heard you say something along the lines of, "Can I have question 2?" because I'm more familiar with that one. And Jan agreed with you. And I don't know whether it was because of you were going to do the solutions for 2 or.
Well, I did the one with the classifying group order 2P.
That's the one I think it was.
Yeah.
You were referring to.
Yeah. No, I like that.
I quite like the amplitude. I like him more than
Okay.
He needs to stop saying, "Oh, it's easy."
Mm.
He says that.
It is to him, though.
Yeah, no, but like mathematicians use the word easy, obvious.
Oh,
Because-
But essentially,
They mean really difficult if you
They
don't
use
lie.
it-
frame of reference.
they use it in a
more of layman's terms.
tongue-in-cheek way, kind of. As soon as you've
I
seen a
can't put my
proof,
tongue in my cheek right now.
Well,
It'll hurt.
as soon as you've seen a proof of something, everything's easy.
But that's the thing. That's for someone who's
It's
arithmetically gifted.
But you should but you should be hardened. You should be steeled to that by now.
Yeah, but it's when someone
I
comes
just
up
like
to
the-
me with a problem, they go, "Jordan, what's 4/3
Yeah.
times like 2 6s or something like that?"
Yeah.
I go, "How do you not know this? This is easy."
Well, that's kind of the way. to do
Or-
it.
When you,
also
when you
you say
compare that killing to
calculator.
this,
It's mean, though. It's still mean.
Okay, so let's get going. So I think this chapter is quite. I was going to say easy. But in because we're not meeting a whole new strange concept here. We're continuing. It's very much just a slight variation on the isomorphisms. Yeah. So isomorphisms, right, was our maps between groups that were extremely nice, bijective, 1-to-1 and up to, and they worked well with the group operations in the two groups. So here we see the same condition again. Remember, we called it the homomorphism property, not the isomorphism property. We called it the homomorphism property because it's much more general. So a homomorphism property is basically an isomorphism when you drop the iso part, when you drop the requirement for bijectivity. Okay, so it's any function between groups that satisfies the homomorphism. Okay. Yeah, but I'm not doing the live broadcast. I'm just recording on the laptop and then I upload afterwards because you get slightly better quality.
Okay.
So I think they
It didn't
throttle.
come up and I was just thinking,
Yeah. No, they throttle the upload a little bit so I get better quality. Yeah. So so here dot is the operation. We only mention the operations just when we really want to be very careful about the roles of them. We only give notation to the operations. We want to be really careful. So dot is the operation in G, circle is the operation in H. So phi is the mapping from G to H. 5G1.G2 is 5G1 circle 5G2. Okay, so that's the mapping, meshing well, integrating well with the two group operations. Another reason why this is easy, so to speak, is, well, a better word than easy, familiar. Familiar is the word. So last year, you spent a fair bit of time dealing with linear transformations, did you? From one vector space to another. Yeah. The property that linear transformations had, well, they had two, well, let's look at one property. When you had a linear transformation, T going from one vector space to another, one of the parts of that was that T of U1 plus U2 was what?
T of U1, yeah, T of U2.
T of U1 plus T of U2, right? So there, this plus is taking place in U, this plus is taking place in V, yeah. And in fact, vector spaces, if you forget about the scalar multiplication, if you just look at the vector spaces and only take account of the vector addition, just ignore the fact that you can multiply by scalars, then what you're looking at are groups. Okay? They're actually abelian groups. Okay? So vector spaces, they've got additional structure, the scalar multiplication and how that interacts with the addition. But if you just focus on a vector space with its operation of addition, they are really groups. So they've got the identity element, which is so what's the vector that when you add it to any other vector leaves it unchanged?
Zero.
Zero vector. Yeah, it's the identity element. Because you hit any vector with it and it leaves it unchanged. Yeah. Just like a group element, in group theory we say G times the ident E equals G. But in this context it's U1 plus 0 is U1. So they've got an identity element. Vector addition is associative. It's one of the axioms for a vector space. And there are inverses. The inverse of a vector is the -1 times the vector. Yeah. So these are examples, and this is exactly the homomorphism property interpreted in this context for these sets with this plus and this set with that plus. So these are our examples, our group homomorphisms. So that's another way where we realize that what we're looking at here we have seen before, even though we didn't use the language of groups and homomorphisms, but we've definitely been looking at this one. Okay. But what we're looking at now with groups, it's much wider. Okay. Vector spaces are examples of groups, but they have lots of other structure to them. Whereas when you're groups, you're only asking for a set with the binary operation on it that satisfies the properties. So it's a much wider, more general concept. Okay. So remember, isomorphisms was this property where phi was bijective, but now this is weaker. So we've no specification about injective or surjective for phi. So it might not be injective, it might not be surjective. Okay. So if you're starting from a group G, we anticipate many more homomorphisms coming out of G rather than isomorphisms. Isomorphisms are functions like this that must additionally be bijective. Yeah. So the extra properties for the function to satisfy. Whereas homomorphisms, we're only asking that this is the case. So in general, there'll be many more functions emanating out of a group G that will be homomorphisms compared to isomorphisms. And you've already been observing examples of these. Okay, so what are some of the initial examples of those? So you've been talking about permutation groups, so the symmetric group Sn. We've seen how you can classify permutations into even and odd permutations. Okay, and we know so even a permutation is even if it can be expressed as an even number of transpositions, and odd if an odd number of transpositions. And there was a theorem about permutations that if it's even, it's always if it can be expressed as an even number of transpositions, any representation of it as a product of transpositions will be an even number of them. You can increase and decrease the amount of transpositions you can express it as. There will always be an even number. And vice versa for odd. If it's odd, it will always be odd. But really, even and odd is really an encoding of the group Z2, binary addition. Group with just two elements, 0 and 1. So even is 0, 1 is odd. So you add 0, 0, you get 0. You add 1, 1, you get 0. You add 0, 1, you get 1. So actually what we have is a homomorphism from Sn to Z2. And if you think about it, why is this? Well, to see that it's a homomorphism, so you've got phi from Sn to Z2, where phi of sigma is equal to 0 if sigma even, and 1 if sigma odd. This example, this is just the first example, 11.1. I mean, why is that an isomorphism? So you got to think of, taking two permutations, sigma and tau. Seem to use these letters conventionally for our permutations. So sigma and tau. If you apply phi to sigma tau, what are you going to get? Well, is sigma after, remember, okay, this is the group operation taking place in Sn. So this is composition of these permutations, sigma after tau. Is sigma after tau even or odd? Well, it depends on whether sigma is individually even or odd and tau is individually even or odd. But the way it depends, if both of them are even, then, so we're just going to check. What we're going to check is we're going to adjudicate this. So this is the homomorphism condition. So we need to check, is it true? Is this true? I remember this operation over here is the operation taking place in Z2. So this is either 0 plus 0 or 1 plus 1, or 0 plus 1 or 1 plus 0. Yeah. Accordingly, as sigma and tau are odd and even. Okay. So there's four possibilities for the even, sigma even or odd, tau's even or odd. So there's four different combinations, isn't there? Yeah. So you just check each of them. If both are even, the composition is even. Because just all the transpositions here plus all the transpositions here. So it's an even number of transpositions. So this whole thing is even. So it should go to 0 under the mapping phi. Is the product of these two 0? Well, if sigma is even, this is 0. If tau is even, this is 0. So you got 0 plus 0. Because this is the group operation from Z2. So you got 0 plus 0. So yeah, the homomorphism property checks out in that case. You check out all the other cases. If sigma is odd and tau is odd, they're both odd. What's sigma after tau? Even. Even. So remember, odd means we can represent sigma as an odd number of transpositions, and tau as an odd number of transpositions. But then the composition you can represent just by joining together the two lists of transpositions. So from an odd number and an odd number, you get an even number. So sigma, so phi of that should be 0, because it's even. But is it equal to this? Well, if they're both odd, these are 1s, and it's 1 plus 1. But in the group Z2, 1 plus 1 is 0. So again, it's satisfied when they're both odd. And then the cases where 1 is even and 1 is odd, the composite is odd. And one of these is 0, one of these is 1. If you add them together, you get 1. So the value is 1, as it should be, because the composite is odd. Okay, so it checks out. Yeah. So all four cases of parity, sigma and tau, satisfy the homomorphism property. So it is a homomorphism. Is it an isomorphism?
No.
Why not?
There are multiple different elements in Sn that can go to 0 and 1.
Yeah. This is very big. There's only two things. Yeah, this is a big one. Except for the case.
Is it Z4? No.
Except for, so what case might be special? In general, this is big and this is small, so it's not going to be bijective. So the special case might occur.
S2.
S2, yeah. How many permutations are there of two objects?
2.
So the identity, you can leave them in the same position, or you can transpose them. So there's actually only two permutations, and the identity, which is by default odd, because it can be expressed as two transpositions, like no transpositions, 0 is odd. And the single non-identity element, the transposition, is. Did I just say the identity was odd?
Yeah.
No, it's even identity. Thank you. I saw that. Question. Look. Yeah, even. But the single non-identity permutation is odd because it's one permutation. So it's the special case. It's an isomorphism when n is 2, but in all the other cases, not. Okay. So when n is 2, an isomorphism. But in general, for n bigger than 2, Sn is large. So not a bijection. It can't be a injection. It can't be 1 to 1 because Sn is too big. Yeah. And not a sorry, so not a bijection. So not a nice. Okay. I think we've done that example to death. As is possible to do. So there's only 2 elements in Z2. Not that much interesting can happen when you do a homomorphism to a group with 2 elements, perhaps. So any questions just about that example and the definition? So the next few examples are maybe more interesting because there's more going on. They're a little bit more general. Can I take that page away? Yeah. So let's look at these examples. 11.1. Take any group, take any element from the group. Suddenly, we've automatically got a homomorphism from the integers into the group. We take any integer and we map it to that power of g. Okay. Is it a homomorphism? Certainly a mapping. Yeah, so here's an integer. This is an element of the group G. So it is a mapping from Z to G. No problem there. Is it a homomorphism? Well, if it's a homomorphism, we want phi of m, combining m and n in Z, so that means m plus n. It should be equal to combining phi of m and phi of n in G. So we just represent that like that. Okay, G is gen. G isn't specified what G is or anything. It's just a general group. So are these 2 equal? Well, the definition of this is G to this power. But then we've already confirmed in our initial work with groups that the power notation does satisfy the usual rules for exponents that we're familiar with from real arithmetic. Yeah? G to the power of m plus n is G to the m times G to the n. Because this just represents this number of G's all multiplied together. And this is just mg's bit of the list and ng's the rest of the list. Okay. So this property of indices of exponents of group elements just holds, okay, by the definition of it. That's with positive m and n. When m and n are negative, it corresponds to positive powers of the inverse element, remember, by definition, so it's the same principle. Okay. The rule of indices just follows. And of course, this is 5n times 5n. So it is a homomorphism. And it maps Z onto the cyclic subgroup of G generated by little g. Yeah? Because we can obtain any power of G. And by definition, the cyclic subgroup generated by little g is just the subset of capital G consisting of all the powers of G. So we can construct a homomorphism from the integers into any group at all by just picking out an element from that group, and suddenly we got a homomorphism from Z into the cyclic subgroup generated by that element. Okay. Another example, matrices, the determinant function. Currently, my second years are doing Steve's question. Do you remember that from factorizing determinants and stuff? Yeah, so this is this property of determinants should be like.
Oh God, yeah, that question.
Flashbacks.
Literally.
I got no marks in that question.
Did you not?
Nope. I got no marks in half of them. No, of course not.
I got the right answer and you said that you've done it wrong.
Yeah, that's what I got.
Okay. Oh, I was curious. I was no one knew how to do it the way you wanted to do it, so we all just found it.
All right. Okay. But You're quite familiar with this property.
Yeah.
Oh, yeah.
The determinant is multiplicative. Okay. Now you originally meet that as just a property within matrix stuff, matrix multiplication. But we can see it as a embodiment of the homomorphism property by the fact that the determinant itself is a homomorphism from, well, any group of square matrices under matrix multiplication. The biggest one we can form, say if we're talking about 2 by 2 matrices, is all the invertible 2 by 2 matrices. That's the general linear group. Remember, by definition, that consists of all determinants with all matrices with non-zero determinant of size 2. So you just look at the determinant function. This gives you now a function from this set of matrices to the real numbers, to the non-zero real numbers. Yeah, because by definition, there's no determinant here with determinant 0. So you never get the value 0 out of this. Okay, so this is going from GL2R to R star. And this, what was already familiar to us as a property about how the determinant operates, now we see it through our group theory classes as it's the homomorphism property. The determinant of a product of the two elements in the group is the product of their images in the other group under the mapping. Yeah. Okay. So that's another example there. I'll leave you to read that. I would like to prove something. Jump on to a proof. So any questions about the definition?
Where can I get a pair of good theory glasses?
Good theory glasses. Well, I'm building them for you in this week by week.
Mini shed at home.
So, proposition 11.4. Now, okay, so I won't use the word easy, but I'll say
No one's going to climb over the tables in a minute.
He's never going to be able to say the word easy ever again.
It's familiar. Some of these things you've seen before, right? Early on in the isomorphism chapter, we kind of quickly accumulated arguments about how isomorphisms preserve group properties, groupiness.
Yeah, that's going to happen.
Look, theorem 9.6. Theorem 9.6, if we had an isomorphism, the two groups have the same number of things in them. G was abelian, H was abelian, G cyclic, H cyclic, G is a subgroup of that size, H is a subgroup of the same size. Okay, the isomorphism maps all these properties back between the groups. The groups have to look the same with respect to whatever group property you talk about. Now, we won't. Okay, homomorphisms are weaker. They don't have as many properties as isomorphisms. They have the key property, which is the homomorphism property, but they are not projections. So we certainly won't expect this thing, that the two things have the same size. Indeed, we've already seen our example from the big permutation groups down to the small 2-element Z2. But certainly, you can have homomorphisms between groups of different size. So we're going to lose that property, of course. Well, maybe some of these. So the question is, what other properties can we rescue? Are there things that are preserved by homomorphisms in either direction? Okay, and there are some, and that's what this proposition 11.4 starts to talk about. So first property is. Will I write this out by hand? No, let's follow Judson. I'm not being lazy, but I'm conscious in some of my other units I've been writing out loads of stuff by hand, and the students are complaining. So let's discuss this and interrogate this. So first of all, homomorphism nicely, it does preserve the identity, or it does do the sensible things to the identity. So if E is the identity in G1, phi has to map E to the identity in G2. So you must send the identity to the identity. Every homomorphism acts like that. And it does the correct thing to inverse elements. So phi of the inverse of G is the inverse of phi of G. Okay. We expect that as well. If H1 is a subgroup of G1, you map the whole set across. So you understand that phi of a subset just means what, the subset over here that contains all the images of the individual elements of the subset over here. So when you map the subset across, it maps across to a subgroup of G2. So that's nice. If your subset is a subgroup, you map it across, it's still a subgroup of G2. That's good. So phi, the homomorphism preserves subgroups. Also, interestingly, if you look at a subgroup over here, now this expression, be careful. This is a slight, be careful what this notation means. Normally when you see function to the superscript -1, it's the inverse function, but not in this case, okay? It might be, but not in case. So remember, these phi's, they don't have to be bijections. So when they are not bijections, they won't have inverse functions. But there's still an inverse map that you can construct, but not on the level of elements, but on the level of subsets. Okay, so if you're looking at, so H2 here is it's a subgroup of G2, but it's a subset of G2. So this is referred to as the inverse image of H2. So where are we here? So phi inverse of this subset H2 is known as the inverse image . And it's defined as here. And this definition is general. This definition applies when you substitute H2 for any subset of the codomain. Okay. So the inverse image of a subset of the codomain is the set of all the elements in the domain that got mapped into that subset. Okay. So this definition makes sense even when phi is not a bijection. Yeah. So if phi is not injective, that's fine. If it's not surjective, that's fine. That's fine. The definition still makes sense, okay? So for instance, it's the set of, so for each element in H2, living over here in the codomain, there could be multiple elements in G1 that get mapped onto that single element. That's fine. They will all appear in phi inverse of H2. Yeah? So everyone's okay with the definition of that? Sometimes people call this the pullback as well. It's like the subset H2 is over here, and you kind of pull it back to G1. Yeah, draw it backwards. When they're talking about maps, they talk about push forward and pull back. So you see, you get a subset over here, you push it forward into the other thing, and you can pull it back as well. Okay, but this says if H2 is a subgroup, its inverse image pullback is also a subgroup of G1. Well, that's nice. Okay, so it does quite a good job of respecting subgroups, in both the domain and the codomain. It pushes subgroups forward to be subgroups in G2, and subgroups of G2, it pulls them back to be subgroups of G1. No mention of the sizes. So remember, for isomorphisms, when we were talking about subgroups, their sizes were the same. So if this was the isomorphism, the subgroup of G1 gets pushed over to a subgroup of the same size over in G2. In fact, it'd be a subgroup isomorphic to the subgroup of G1. That's the same isomorphism. But here, the sizes could be changing. So in particular, when you push forward a subgroup, the subgroup in the codomain could be much smaller than the subgroup it came from. Yeah, it couldn't get larger because phi is a mapping. So it only, if you give a phi an argument, it just gives a single value to it. But it can collapse down elements to the same image. So it can make your subgroup smaller as you push it over. Similarly, when you pull back a subgroup, it potentially might get bigger. And potentially might get smaller too.
But then that would indicate that it's going from a small to a large.
It would yeah, so that's, well, here's the thing. So
yeah, therefore it's not one-to-one.
Yeah, but it doesn't have to be one-to-one.
Yeah.
Right.
It's not one-to-one.
Because it's a homomorphism.
Go back to different things.
Yeah. So it might get bigger,
Yeah.
and it might get smaller.
Jeez.
So it just depends on what the mapping is.
Right.
Yes, squaring
If you square root,
numbers.
square root, you can get the
Yeah.
positive and negative root.
Yeah.
That'd be-
Yeah.
Well, you can't
4
add a
goes back
negative.
to -2 or 2.
Or think of the determinant example. So this here. So maybe one subgroup. Okay, for instance, okay, a small subgroup of R star, say the subgroup just consisting of 1 and -1. Special cases. So it's a small 2-element subgroup of R star. It's closed under multiplication.
Yeah.
-1 by 1 is -1. So it's -1 squared is 1. So it's a closed system. But how big? So it's a subgroup over here, so we can pull it back, take its inverse image.
Yeah.
How big is the subgroup over here? Well, it's every matrix with a determinant of +1 or -1.
And there's quite a few of those.
Quite a few of those. Yeah. Many of those. Because if you have A and D is 1, and C is 0, then B can be any value at all.
Yeah.
And it will have determinant.
Yeah, is that like
So it's
infinite?
infinite.
I think that's the question we did the other week.
Yeah, I was going to say that.
Yeah, that set of matrices was closed under multiplication. So it was a sub. So now we can prove it by the fact it's the inverse image of a subgroup under the determinant homomorphism. It's a roundabout way of proving that.
Saying that sentence to anybody in my local area, a spring would pop out of their ear.
But you know what I mean.
Yeah, oh yeah, no,
Yeah.
totally, I
Good,
understand.
good. So the small subgroup in R star can come from a huge subgroup in GL2. Okay. Or it might have come from a very small one. But this phi is surjective. Everything in R star occurs as a determinant. So the subgroups will always get bigger.
Yeah.
Potentially. Yeah. Yeah. Every element of R star has an infinite number of pre-images over here. Yeah. So it's never the case that the subgroup over here will be smaller. You can object to that? Or?
No.
No. It just looks like
Don't worry.
you were leaning forward with a pen. You have an objective stance.
That was magical.
Feel the
Okay.
block slowly after.
Okay.
It's going again.
Oh no. What is that?
Alan, stop using your magic. Stop with the pops.
Yeah, well, that was the only special effect.
Yeah.
Just a slow zoom into.
It's
It's
as if that was an effect. It's just
It
a
was
man
just
walking
that.
further closer and back from the
That
stage.
guy must have been on drugs for doing that so quickly.
Okay. So actually, I think let's talk. Okay, what's involved in proving these? The identity one, I think, is just proved the same way we proved it for isomorphisms. So it says. So here it says, well, suppose E and E prime are the two identities. E over here, E prime over here. So he does this in a kind of a clever way. We're asking what is phi of E? Yeah, that's the question. What is phi of E? What is phi of E? Well, we know it's the same as E prime times it, because this product is taking place in G2. E prime is the identity. So we know phi of E is E prime times phi of E. We can think of E as EE, the identity times the identity. So by the homomorphism property, that must be phi of E squared, phi of E by phi of E. But then you're looking at this, then the equation from the left to the right, we can cancel the element phi of E, whatever it is. Because in any group, you can do cancellation of things. You multiply both sides on the right by the inverse of phi of E, whatever that happens to be. But it does have an inverse, because it's living in a group. Okay. So you cancel those, and then you get phi of E is E prime. So it kind of has to be. If your phi is satisfying the homomorphism property, it has to send the identity element to the identity element. It might send many other elements to the identity element as well, but it must at least send E to the E And the inverses follows again from homomorphism property quite quickly instead of easily. So it's relatively quick. So, I mean, we're testing out what is phi of G inverse here, right? We're looking at the product with phi of G. We suspect it's the inverse of phi of G, but we're trying to prove that that's the case. But the homomorphism property, we can say it's phi of that product, yeah? G inverse times G. That we know is the identity because this is the product of G and its inverse in G1. So that's E, the identity in G1. We've just proved a second ago phi of E is E prime. So the product of these two is E prime. So that means this element here must be the inverse of this one. So in effect, that -1 superscript can come outside. That's what that demonstrates. Okay? Yeah. 3 and 4. So 3 is that the push forward of a subgroup is a subgroup. Okay, so you start with a subgroup H1 of G1. So the statement said start with H1 of G1. And we want to prove that this subset, okay, phi of H1 is certainly a subset of G2. We know it's not empty because it at least contains the identity. Because the identity is present in H1. So phi of the identity, which we just proved is the identity in G2, is present in phi of H1. Okay. So it's a non-empty subset. So then we consider two elements in it. Now we want to prove closure. X times Y must also be an element of that subset. And it has to come from the homomorphism property. Or actually, he's using the second form. So proposition 3.30 was the first subgroup theorem, which said, check that the identity is in it, it's closed, and it contains all inverses. He's using the slightly, I don't prefer this that much because it kind of compactifies it. But the second proposition said to prove a subset is a subgroup, show that it's non-empty and that this kind of mixed closure statement holds. For any two elements X and Y in it, the product X times the inverse of Y is in it. Okay. If you look up proposition 3.1, it's the compactified subgroup theorem. It kind of joins together the closure statement and the existence of inverses. I actually prefer it. It's clearer. Anyway, let's look at this. Well, you see, X and Y are in here. Well, you know, to really exploit that, you need to emphasize that they are in here. So they're in here if they come from something in H1. So we have to name those objects. Okay, so X has come from something called A, Y has come from something called B. And these A and B live in the subgroup H1. Okay? We know that. Assume X and Y are in 5H1, we know there are these corresponding A and B. There might be multiple choices of element for this A here. So it could be many elements sent to X and similarly for B, but we just make one choice. And then we think about X times Y inverse. We're trying to prove it's in 5H1. Well, we rename these things in terms of A and B. So X is 5A. B, what Y inverse is the inverse of 5B. And that's, we just proved that in part 2. But homomorphism property, well, first, he's actually skipped it out here. You see, there's an intermediate step. There's an intermediate step where he takes the inverse inside. So to make it phi of inverse of B. And then you can apply the homomorphism property to say it's phi of A times the inverse of B. Yeah. So there's actually, you could think about it, an intermediate expression there, which is phi of A times phi of the inverse of B. Yeah. Then now apply the homomorphism property to give you this. But H1 is a subgroup, so AB inverse is again in H1 by proposition 3.3. So we know H1 is a subgroup. We're using that fact. So if AB inverse is in H1, then when you apply phi of it, you, by definition, end up in phi of H1. Yeah, so that's the definition of phi of H1. It's anything from H1. So this product, this mixed kind of inverse product thing, xy inverse is in phi. So by proposition 3.1, it is a subgroup. Yeah. Pullback. Pullback seems, the inverse image seems to oh, did he add on the normality? Ah, yeah, the furthermore. I forgot the furthermore bit. This is interesting. This is we're going to use this. We'll be using this tomorrow, I believe. Not only is the pullback or the inverse image of a subgroup, but if the H2 that you're taking the inverse image of, if it is normal in G2, then its inverse image is also normal in G1. In normal subgroups are these nice special groups that we can simplify the group with. We can take these factor groups that Jan was teaching you about. Okay, so they're useful and significant subgroups. So question 4 proves this. So this is why I'm looking a bit longer, because it's addressing the normality as well. Okay, so we just do the proof in the opposite direction. We start off with H2. We know we assume it's a subgroup of G2. H1 we define to be the set phi inverse of H2. So at the beginning, all we know is that this is some subset of G1. Yeah, remember phi inverse of H2 is the set of all little g from G1 such that phi of G is in H2. So at the moment, it just looks like a subset of G1. Yeah? It is by definition a subset of G1. So we just have to prove it's a subgroup. So again, he's going to use proposition 3.31, I presume. He doesn't quote it there because he's just used it before, so he's going to use it in the same way. So we need first to prove that this is a non-empty subset. And it is non-empty because the identity is always the answer to these questions. I mean, because the reason it's always the answer in these general argument type questions is if I say that's a group, and if that's all I tell you about it, what's the only element you can point to that you can name? The identity. That's the only one we know we can definitely talk about.
There can't be a group of nothing.
Yeah, because groups are by definition non-empty.
Yeah.
Yeah. I mean, you could allow the empty set to be called a group. The most boring group in the world. Even more boring. At least the identity element, the trivial group, has something in it. It's rather spiritual. It's got one thing in it. But yeah. So and that's the reason why the identity occurs so often in these kind of arguments, because it's the only thing we can point to if we have no other information. Okay. So the identity element is in here. Why? Because we've already proved that phi of the identity is the identity. And H2 is a subgroup, so it contains the identity element. And phi must send the identity from G1 to the identity of G2. So the identity of G2 is inside H2, so therefore the identity of G1 is one of these little g's. Yeah? It qualifies as one of these little g's. So phi inverse of H2 is non-empty. So then we got to prove this mixed closure condition. Yeah, so we take two elements from, oh yeah, he's defining H1 to be, he defines H1 to be that. So take two elements from this, A and B. Well, if you take two elements A and B, then then phi of A and phi of B, they both live in H2 by definition. So that mixed inverse product thing, the first element times the inverse of the second, it is in H2 because H2 is a subgroup. Yeah. But this product involving the inverse by the homomorphism property and the inverse property, it is phi of AB inverse. Okay. But we've already just said this is in H2, so this is in H2. So AB inverse is something that gets sent to something in H2. So AB inverse qualifies as one of these little g's that is in the inverse image. Yeah. So by proposition 3.31, H1 is a subgroup. Not only a subset, it is a subgroup. It's non-empty and it satisfies this closure and inverse property mixed together. So that brings us to here. H1 is a subgroup, and then we address the normality condition. So again, prove the idea, the technique here is very much like all the other arguments. We assume that H2 is normal, and just look at how phi brings that normality right to, well, we might have to make a choice about which characterization of normality we're using, how that pulls it back into G1. And so the criteria for normality is using is this closure under conjugation. So remember, N and G, if N is a subgroup of G, N normal in G, if and only if for every little g, when you conjugate, when you conjugate the subset, it's equal to N. Or in other words, for every N in N, G and G inverse is contained in N. That's another way of saying it. So you take any element from the proposed normal subgroup, when you conjugate it by any other element from the group, that conjugate must still be in the subgroup. If the subgroup wasn't normal, this could sometimes bring you outside of the subgroup. Okay. So normal groups are special in that they contain the conjugate of any of their elements by any other element from the group. So it's this elementhood property that he's going to prove. So except he's got the inverse in the first element, but that's without an equivalent thing, because this thing is ranging over every G and G, so it doesn't really matter where you put the inverse, because equally well, as little G ranges over all the elements of G, so will little G inverse go through all the elements of G. So he's going to prove that the conjugate this way is contained in H1 for any H in H1 and any G in G1. How can you do this? Well, you just hit it with the homomorphism property and see what happens. So you look at a conjugate of this little h, apply phi to it. By applying the homomorphism property and the inverse property, we can express it like this. It's the product of all the individual phi's, and the phi of this G inverse is the inverse of phi of G. Okay. But then this, what does this look like? This looks like the conjugate, because you're pre-multiplying by the inverse, post-multiplying by the element. Yeah, it's just the other way around from that, so it's equivalent. This is the conjugate of this element phi of h. But phi of h lives in H2, because the h lives in H1. The little h lives in H1, so the little h is something in the inverse image of H2. So when you apply phi to it, you land in H2. But we've assumed H2 is normal, so therefore the conjugate of it by any other element of the group is in H2. And if it is in H2, it came from applying phi to a conjugate. So therefore this conjugate is also in the inverse image. So this conjugate element also lives in H1. Okay, I've gone a few minutes over there. Sorry, but that ends that proof. Okay, so we'll leave it there for.